In this video, I'd like to talk some about a little bit more about big O notation and sort of like how to do this, right? And sort of the concepts behind like looking at functions and determining what the big O is of those functions, right? Remember that big O, it represents the worst case running time. And it does so based on the size of the input, right? So we're going to be looking at functions, and we're going to be looking at them with the idea of how does the size of the input change the runtime of these algorithms, right? The time complexity, right? Time complexity. And remember that you can also do this for like memory complexity. Right? You can also do this for memory complexity, but we're not going to focus on that right now. Okay, excellent. So let's take a look at some functions. First, let's look at, let's see, some function that looks like this, where I have int a, and actually, let's make this a little bit more clear. And let's call this, let's call it int n, right? To make it a little more clear. Okay, so n is sort of like the size of our data. So let's start with something really simple. Int a is equal to 1, a equals a plus 2, and then return a, right? That's it. That's our entire function. A is equal to 1, a is equal to 1, a is equal to a plus 2, and then return a. So now the first thing we're going to do is we're going to look at these blocks, these like lines of code here, and we're going to figure out how long do these things take to run based on the size of our input, right? So this one here, is this going to change based on the size of our input? In this case, the size of our input is just the size, like the value of this number n, right? So n could be 0, 1, 2, 100, 1,000, whatever, right? This is the size of our input here. It's just the value here of n. Well, no matter what you pass in for this value, this line of code will never change how long it takes to run, right? This line of code will always take the same amount of time. That means that this line of code is constant time. Big O1, right? Constant time. This is a constant time operation. Let's look at the next one. A is equal to a plus 2. Well, this one is also not going to change. It doesn't matter what that n value is. This is also constant time. And then we say return a. Well, this isn't going to do anything. So this is always going to take the same amount of time. So our function here is equal to big O of 1 plus big O of 1 plus big O of 1, right? Now, if you have 3 constant time functions, right, that are all being added together, right, this can be simplified. So essentially it can be simplified because we don't care how many constant time operations there are, and we just say that this is a constant time function, right? You can essentially just combine these things and say, you know what, big O of 1 is the same thing as, 8 times big O of 1, right? It doesn't matter that we run this function 100 times. It's all going to take the same amount of time, no matter the size of our input. So we just say like this is big O of 1. So this function here, this first example, is a constant time function. It will never change based on the size of our input. Cool. Let's look at another one, slightly more complex. So what if I do something like this? Say I do 4 int I equals 0. Well, I is less than n, I plus plus, and I do something like print hello. Real quick, really easy, right? Oh, my last function returned a value, and this is a void function. That's a mistake. Who's going to correct me on it? All right. 4 int I equals 0. Well, I is less than n, I plus plus, and then I'm just going to say print hello. All right, so the question is how long is this going to take to run? And the way that we sort of break this up is the first thing we do is like, let's look at what's inside of our loops here, right? So we want to break this down into individual statements. Let's look at this statement here. This statement here, print hello, this is going to take constant time. It is never going to change how long it takes to print the word hello based on the size of our input, right? Well, this one here, this for loop, right? Our for loop is what? Let's see. If our n is 1, this is going to be 1 iteration. If our n is 10, this is going to be 10 iterations. If our n is 100, this is going to be 100 iterations, right? This is linear time. This is linear, right? Which means that as the size of our data increases, the amount of time it takes to execute this increases linearly with it, right? If we were to graph this, it would look like this, right? And the value of 10 takes 10 iterations. The value of 100 takes 100 iterations, right? And it sort of looks like this upward sloping graph, right? So we have big O of n, right? And for each big O of n, it's doing a constant time operation, right? Now, this technically is something that looks like this, big O of n times big O of 1, right? Because it's doing, for each of these, it's doing the constant time operation. Well, in this case, when big O of n is multiplied by a constant time operation, we can simplify it and just say this is big O of n, right? We don't care that it's some constant time operation there as well. This function is going to increase linearly based on the size of our input data. So this function is linear, right? This function here, our for loop, and most for loops that loop while they're less than the size of the data, right? This thing here is going to be big O of n, right? This is linear. Cool. Let's do another one, slightly more complex. What if I do something like this? For n equals 0 while I is less than n, and then I say for int j equals 0. Well, j is less than n, right? J plus plus. And then I do print hello. It looks something like that, right? Let's break this one down. First, here at the very beginning, or here in the very middle, this is big O1, constant time, never gonna change. This loop here, well, it looks just like the loop that we just did. This one is big O of n, right? Just like the other one. Starts at j is equal to 0, well, j is less than n, it's gonna increase the size of the data, right? Now let's look at this one. I is less than 0, or I equals 0, while I is less than n. This one is also gonna be big O of n, right? Now what do we have? We have big O of n times, because it's doing it for each one of these operations, it's doing a set of these operations, which is why it's times, right? It's multiply. We have big O of n times big O of n times the constant time one, right? Well, we already know that big O of n and constant time 1, this simplifies to big O of n, right? So we essentially have big O of n times big O of n, right? Which is big O of n squared, right? This thing is going to increase according to a graph that's going to look something like this, and it's going to shoot up, right? It's going to look like a parabola. And that's because this is big O of n squared. This thing is going to get like progressively worse and worse and worse, right? So this double for loop, the for inside of a for loop, is really common to see while it's looping less than the data. And it's really quick and easy to see like, okay, this is big O of n squared, right? Now let's imagine another case. Well, what happens if I put another for loop in here that's like for int k equals 0? Well, k is less than n. K plus plus dot 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 dot, and I put a constant operation in there. Well, the only thing that's going to change is the number of linear operations I'm going to do. This would then become n cubed, right? Which just means it's like an even worse looking parabola, is really what that looks like. So this is sort of like these embedded for loops in on each other, right? Now let's do a couple other real quick gotchas that we got here, right? Say I have a function that looks like this. For int, let's say int j equals 0, and then I do a print hello, right? Something looks like this. We know this is n squared, right? The for loop and the for loop. Well, what if I do something here that I'm like, if n is less than 100, then I just return 0, right? Or I just return. Sorry, this thing's not returning anything. It's a void function. Then I just return, right? If n is less than 100, then return. Well, this here is actually constant time, right? And then this, we know, is n squared, right? Well, remember, big O is the worst case runtime. This thing, we don't care about that. This has no impact on the worst case runtime of this algorithm. This function is still n squared, right? This is still n squared. This does not matter, right? Keep that in mind. You're always looking at the worst case scenario, right? You could do something like this, where you say, like if n is equal to 1, then do these double for loops, right? So only in the case that n is equal to 1, I mean, I guess this is a little specific because really it means that this would be 1 and this would be 1, right? But you get what I'm saying, right? Like this, like when we look at our algorithms here, we only care about the worst case, the worst possible outcome. That's what we're looking at. We're always looking at the worst possible outcome. And that's what we want to compare them to each other, is the worst case scenario, right? Cool. Let's do one more example. What if I had something that looks like this for, let's see, int I equals 0. Well, I is less than n, I plus plus. And I do something like this. I'm going to create a vector of integers. I'm going to call it v. I'm going to do v dot pushback I. What is this? What is the worst case runtime of this function? I'll let you think about that for a second. Well, let's break it down line by line. First, what's this one? This one we know is big O of n, right? It's linear. What's this one? Well, it's only one line of code. So it's constant time? No. You're calling a function here, pushback. It's whatever the worst case runtime of this function is. In this case, the pushback function on a vector is actually big O of n. That's the worst case runtime of this thing. It's linear. So what is this thing? N squared. Big O of n squared, right? Even though there's only one for loop here, because we need to consider the worst case of the worst case runtimes of our functions that are inside of our functions, right? Cool. Keep these things in mind. So this is just a real quick primer on sort of like how you would look at a block of code and sort of deduce what the runtime would be, the time complexity would be of those functions using big O notation. And remember the other method is sort of just like actually coding these things and looking at the runtime empirically, which is also incredibly effective. But this is how you'd sort of do it the long way and how you do it by hand.